theorem for x plus 1 to the p are given by p choose 0, p choose 1, p choose 2 binomial theorem. So like this. So this is like, oh, I'm an idiot. So yeah, this is 3 choose 1, 3 choose 2, 3 choose 3, 3 choose 0. So these are the binomial coefficients. But the point of this is the ones cancel, and you've just got x to the p minus 1 plus px to the p minus 2 plus dot, 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 plus p like that. And all of the binomial coefficients I'm not writing, if you study the formulas for binomial coefficients, they have a factor of p in them. So if you study binomial coefficients, p choose something has p as a divisor. So p divides all of these. All the coefficients here. Of course, p does not divide 1. Therefore, by Eisenstein, phi sub p of x plus 1 is irreducible over q, right? Think about it, though. What would happen? Suppose for a second that phi of x is reducible. Is that possible? Could that happen? If phi of x was, if phi sub p was, if phi sub p of x was equal to, like, g of x times h of x, then phi sub p of x plus 1 would be what? G of x plus 1, h of x plus 1, right? But that's not allowed by our argument by Eisenstein. Therefore, phi p is irreducible. Phi p of x is irreducible. This is a shifting trick. Like, you can take a polynomial you're looking at and you can shift it like this. And if you can prove irreducibility for the shifted polynomial, you still get irreducibility for the original one. This is a sneaky trick, but it works for this one.
Is it because it's over Q, though?
No, I think that the shifting theorem works elsewhere.
Like over any field?
I don't think that. I think the argument I just went through is field independent. Yeah, I mean, as far as I can think, I think that might even work not even over a field, but over just an integral domain. So theorem. So f of field and p of x and a polynomial over the field. All right. Then the ideal generated by p of x is maximal ideal if and only if p of x is irreducible over f. So now we are connecting our previous discussion of maximal ideal with our current discussion of polynomial factoring. This is exciting. Now for the proof. All right, so suppose f is a field and p of x is polynomial, right? If the ideal generated by p of x is maximal in the polynomials, right? Then that means that p of x is not equal to 0, right? And thus p of x is not equal to 0, right? and P of x is not constant, right? How do I know that P of x is not constant? So if it's a maximal ideal, so I believe we
Is it, oh, wait, no, we're trying to prove that.
so I believe our definition of maximal ideal requires that it's not the whole ring. So if P of x was constant, right? If P of x is equal to a constant, then the ideal generated by C is just everything. Because the ideal generated by, constant multiples of polynomials is all polynomials. So like if you had P of x as a constant, you get everything. So, all right. So suppose P of x is g of x times h of x, right? Suppose that is a factorization over f, right? So in other words, g of x and h of x are polynomials. So if we had j of x was an element of the ideal generated by p of x, then what? Then j of x is equal to p of x times k of x, right? Which is equal to what? Well, p of x, remember, is g of x, h of x times k of x. I'm really starting to regret writing the of x here for the elements, but it is what it is, so I'm going to stick with it. This argument would be like much easier if we just wrote p and g and h rather than p of x, g of x, h of x. You know what I mean? The of x doesn't really add anything to the argument, does it? But anyway, I'm stuck with it. So, all right. So then what? What does that say? Thus, j of x is in the ideal generated by g of x, which implies that the ideal generated by p of x is a subset of the ideal generated by g of x, right? Is a subset of course, f of x. So by maximality, what do we have? We have two things, right? Either p of x is equal to the ideal generated by g of x, right? Or we have that the ideal generated by g of x is in fact equal to the whole set of polynomials, right? If you have an ideal which is between your maximal ideal and the whole ring, it's either that they're equal or it's the whole ring. That's the definition of maximality. So if p of x ideal generated is equal to the g of x ideal, right, then g of x is an element of the ideal generated by p of x, which means what? That means g of x is equal to p of x times q of x for some polynomial q. So what do we know? Let's put it all together here. we have this, and we also have that, right? So what's that tell us? In terms of like, look at the degree there. What do you glean from degree? So the degree, man, stupid red marker. So this one says the degree of P of x, right, is equal to the degree of G of x plus the degree of H of x, right? But this one says the degree of G of x is equal to the degree of P of x plus the degree of Q of x so this one says that the degree of P of x is less than, rather the degree of P of x is greater than the degree of G of x, right? So let me add a condition here, non-trivial. What I mean by non-trivial is not containing a unit, right? It's a genuine reduction. I could cross out the word factorization and say reduction. Just to, all right. So reduction means that G and H are both not units, right? Which means that they have degree 1 or larger. So if these have degree 1 or larger, then it must be that the degree of P is larger than the degree of G. See, because it's this plus that. So it means degree of P is larger than degree of G. But this over here says the degree of G is what? Is larger than the degree of P. Right? So what does this do?
There's a lot of contradictions.
Right. That's a contradiction if, so I suppose that this is if this is a reduction, right? Now notice that if I don't assume that this is, so what's left is that if G of x can be written like this, it must be that Q of x is a unit, which says that G of x is a multiple of P of x. All right? So if that's the case, then
If it's multiple, though, you still couldn't have varying degrees.
yeah, let me finish this up here as fast as I can. We're this far into it, I should finish it. So I went a slightly different direction in the, I mean, what I've written is not wrong, it's just not to the point. So here's the argument I give. So I mean, so rather than, so don't assume it's a reduction up here, okay? Just let it be a factorization. So I'm allowing the possibility that they're units. And then the same things I just wrote give us that the degree, oh, I'm an idiot. Degree of, it's almost the same thing I just went through. The degree of G of x is greater than or equal to the degree of P of x, right? And the degree of P of x is greater than or equal to the degree of G of x. Right, therefore, the degree of P of x is equal to the degree of G of x. Right? What does that do for you? That shows you that.
One of my maximalities on first one is true.
I mean, what does it mean if the degree? So this.
P of x is 1.
Yeah, let me see here how to say this. Well, it means that this up here was not a reduction.
No, it's multiple.
Yeah, but more to the point, it means that this was not, this is what I should be pointing at. This is not a reduction. Right? And the thing is, that's an arbitrary reduction. I've shown for that arbitrary reduction, in case 1, it's irreducible because the degrees are equal. If the degree of G and P are equal, that means H must be a unit. So it's not a reduction. Now, what's the other case? That's the field, right? So else, G of X equals to the whole field, right? So that means that there exists, that means that there exists I need another letter. I'll say A of X in the field such that, right? A of X times G of X equals to 1. 1 is in here. If these are equal, there has to be some element in the ideal generated by G which gives you back 1, which shows you that, in fact, G of X is a unit. Constant, right? And if G of X is a unit, again, we have proved that the reduction fails to be non-trivial. So this proves maximality implies irreducibility. All right? So I hate to leave you hanging here, but the other half of the proof we'll have to do next time. It's not much, right? Like the other half is shorter. But, and then we have like corollary 4.6. We're almost to the end. We're about a page from the end of this one again. So we'll probably finish it up in the next first 10 minutes next class, something like that. But once more, I should remark, this is a good test question. But this one's...
This last theorem?
Yeah, this last theorem actually is a good test question once you don't get... Like, I made this look harder than it is.